At the top of our notes here, we can see I'm focusing in right here, right now, folks, okay? So be there with me. After you decide which model is the correct one for the data set, then you're going to have to write the function. Well, if you've decided that it's linear, then we're going to be able to write it in slope-intercept form. Remember our y equals mx plus b? What does the m represent in that function? Oh my goodness, I know that linear functions were worked with more last year. We should not have forgotten what m is representing. Slope. Slope, yeah. M is slope. What's the slope of the line? And what's the b representing? Where it's starting at, the y-intercept. Okay, so when we do this, what we're going to be doing is we're going to be looking for what's the slope of the line, and guess what the slope of the line is? That constant difference that you find. So if we find a constant difference of 3 becomes our slope. And the b, the starting value, remember the starting value is always where x is equal to 0. So we're going to look what is the y value when x is equal to 0, and then we'll be able to identify our b, our starting place. And then the quadratic formula, here's the function for the quadratic. I have some good news for you. This one's a lot harder, and they don't make us have any of these, but we are just going to quick review the quadratic function. Okay? They're going to give us data sets. When we have to name the model, when we have to give the equation of it, they're going to be kind to us and not give us quadratic ones because those equations are much harder to write. Okay? So let's just do a quick review though of some of these things in the quadratic function. Y equals ax squared plus bx plus c. Anybody remember what the a does in the quadratic model? Don't be working ahead. Stay with me right here. Because you have a semester final to take again. You can trust me, this quadratic stuff is going to show up on it. So what does the a do in the quadratic model? Does anybody remember?
Isn't it?
There's a couple of roles. Think about it. First of all, what's the shape of the quadratic equation?
No, it's the parabola.
Yeah, it's the parabola. It's the U-shaped graph.
And it's the vertex.
Well, there's a vertex in it, yeah, but is the a vertex?
It's where it touches the x-axis.
The vertex might touch the might sit on the x-axis. Okay, we have forgotten. When a is positive, what will the parabola do?
Oh, it determines if it goes up or down.
Oh, yeah, it'll determine if it's opening up or down. So if it's positive, it opens up. If it's negative, it opens down. And then we also did some stuff a little bit with transformations, and we said the larger the absolute value of a, the skinnier the parabola gets, and the smaller the absolute value of a, the wider it gets. We did some of that. And then, do you remember, we identified, what is C in there? What does C tell us in the quadratic model?
We're across the
We're crossing the y-axis, the y-intercept. Just like the b in the linear model is telling us where is it crossing the y-axis? Where is it actually? So for that would mean x is equal to what then? 0. Okay, we certainly don't remember a whole lot about the quadratic anymore. We move on to something else, and the other stuff gets like, does it go to recycling bin or something? Where does it go? Okay, and then our exponential model, our most recent one. Boy, you better be able to answer some questions about this. Y equals a times b to the x power.
Starting point.
What's the starting point? A or the b? The a. What's the b?
Common ratio.
The common ratio, that constant ratio. Okay, so we'll be able to set up our models knowing those two things. Okay, here's the example one that they did. They had this data set here. It's about computer software. And the year is going to be the x values. You can see they put them in a table right here. And they said x is going to be the year number. And the cost is going to be the y's. So then they did the adding subtracting way to see if there were constant differences first. Well, the first differences weren't constant. So then they went on to do the second differences and found out they weren't constant. So that ruled out which two models? Which two models got ruled out? The first differences weren't constant, and the second differences weren't constant.
Quadratic.
Linear and quadratic, yeah. So now we have to move on and say, well, then is it exponential? And so then, now they do, so if you do this on your calculators for me, please. Will you see a $58.32 divided by $64.80? Will you see if that comes out to 0.9?
Yes.
Okay, we'll check out the other ones. Now do 64.80 divided by the previous one, $72, and see if it comes out to 0.9. That's how we find these, right? Yeah, but they don't just automatically, we look at that and we say, oh, you multiply by 0.9. How many of you could have done that? Oh, to get from 80 to 72, you multiply by 0.9. Anybody that good in here? Not even me. That wouldn't even be my thought process. I would have said instead, I got to do 72 divided by 80, and then I would have found out that, yeah, it divides out to 0.9. So we find the constant ratio by doing division, and that constant ratio, it then becomes like the multiplier. So in other words, if we wanted the next one in the table, what would we do? If we wanted the next ordered pair in this table. If I said to you, I want you to find when x equals 4, what would you have to do?
Yeah.
Okay, let's try this again. Brian, would you join us also, please? If I want you to extend this table for me, now that we figured out what kind of a model it is and what kind of patterns going on, and I want you to find the y value when x is equal to 4, 52.49. And
Oh, I went
Oh, you
down.
take 53.32. and
No,
take it
58.32
Yeah,
times
58.
0.9.
yeah, you just multiply it by 0.9 again. And Cassie, you said, I don't know why it went down, but look at what's happening in the table.
It is going down, yeah, I just
It is
looked at it
going
too, I was like, wait, why did it go down again?
Yeah, it is going down. That's a good thing that we got an answer that's smaller than $58.32, or I think this is representing money, I don't know, but
Yeah, it is.
yeah, cost, okay. So then, notice, after, that was just like a little sideline, I want to make sure that you guys are, trying to use some thinking skills. Now it says step 2, write the function. So it's an exponential function, so we got to use the model y equals a times b to the x power. They put in 0.9 for b, the constant ratio, and then they substituted the ordered pair 0, 80 in for x and y, and look at what they got for a. What did they end up with for a? What did they end up with for a?
80.
80. Did they have to go through all that work? No, what would we have done? We're smarter than that. What would we have done?
Left it as it was.
What do you mean left it as it was?
Or you
Explain
plug
that.
an A in for. You would have got your A from when your X was 0.
Yeah, we would have gone to our table and said, oh, well, look over here, right there, when x is equal to 0, right here, where x is equal to 0, right here, where x is equal to 0, that's our starting amount, that's our a value. We would have worked that hard. But what they're doing is they're showing you, which I did not do before, actually we kind of did. But what we can do is if we didn't have an x equals 0 in there, we could do exactly what they did right here. We could take an ordered pair from the table such as 2, oh that's an ugly one, let's take 172. We could take that and substitute into our y equals a times 0.9 to the x power. We could have put 1 in for x, and we could have put the 72 in for y, and we could have solved it and we would have gotten 80. Let's just see if it actually happens, if we can make that work. So we're going to put 72 in for y, and we're solving for a, 0.9, we're going to put 1 in for x. What is 0.9 to the first power?
0.9.
0.9, okay? So now we have a times 0.9. What do we have to do to get a alone?
Divided by 0.
Divide by 0.9. So we'll divide both sides by 0.9, and is 72 divided by 0.9, 80. So we would get 80 equals a. We could have still found it if it wasn't in the table. We can use another point from it, and we can find it. But when it's in the table, we're not gonna work any harder than saying, oh, when x is equal to 0, y is equal to 80, so my a value is 80. Okay. Okay, let's go down and do number 1 here together. Describe the model that best fits the data below, then write a function to model the data. Now, I have a little secret for you. I already kind of shared it. They're not going to make you do any quadratic. They are too hard at this stage of the game for us. So it's either going to be linear or it's going to be exponential. So let's look for a constant first difference. See if there is one. So the x's are doing what? What are they doing first of all?
Goes up by 1.
They're going up by 1, so that's a good thing. They're going up by the same amount. So over here, what's happening?
Times 4. Times 4.
Oh, you think you're going straight to the times 4. You can see, you're not going to do the...
Yeah, you can see that it goes up by 4.
Oh,
so
you can
it's
already
easy.
see it goes up by 4, so you're saying times 4, times 4, times 4?
Yeah.
Everybody agree? Because if we had done the adding or subtracting way to get from 1 to 4, it goes up 3.
Oh, just kidding.
To go from 4 to 16, it goes up
Like 12.
It's like 12, so we have already thrown out that it's linear, haven't we? And I've already thrown out that it's going to be quadratic because we don't, they're going to be too hard. So we're going to say exponential. Now you're not going to just get to write the model without identifying the parts first.
So would you actually want to fill in the equation?
So what I want you to do is first of all, I want you to say what is A and what is B, because we know that the model for an exponential is this. So what's our A value? 1. When x is equal to 0, y is equal to 1,
B is 4.
and b is 4, the constant ratio.
Is that all our worksheets today?
So now, might be. So now the function is what? We're going to substitute that a and that b in there, so we have y equals
1 parentheses 4 to the x.
Now, I'm going to share something with you to just make sure that we're going to put this in our notes too. They might show the answer in the answer bank like this. If you were doing a multiple choice test, let's say, they might do this, but they also might do what? What's another way you think they might give this? It would mean the same thing.
4.
Yeah, just 4x.
Yeah, they would ditch the 1 because multiplying by 1 doesn't change anything, does it? So it's this or this one. I wouldn't count either of them wrong, but I want you to know that if you're taking a standardized multiple choice test and you say, oh, my answer isn't there, you would understand that this means the same thing. Okay? Any questions? So, what we did yesterday, now we just have to write the model for it. Identify the proper parts. Okay, so let's do this one. What do you think is happening here? First of all, what's happening in the x's?
Adding by 1.
They're going up by 1. Okay, that's good.
You're adding by 3.
That one, to get from 7 to 10, it goes up 3. 10 to 13 goes up 3. 13 to 16 goes up 3. So this is linear then, because it's a constant first difference. So we have a linear. What's our model for linear?
Y equals mx plus b.
Y equals mx plus b. Now, I have to clarify something that I might have left a little bit too big a gray area where there could be a change. When x's are going up by 1, this is when x, in fact, let's put that right here. Let's write that in our notes. You guys have room underneath there. When x goes up by 1, M is the constant difference. So whatever is happening to y is that constant difference, that's going to become our M. That's only when x is going up by 1. Because here's the deal, this is really happening. Remember slope? rise over run. Remember that back in linear functions, rise over run? Y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Anybody remember that? Sound familiar? Okay. So what's happening here is this is saying that between these 2 points, it is rising 3 and it is running 1. Well, what happens when you put 3 over 1? What does it become? 3 over 1. 3. So every time we really have here 3 over 1, 3 over 1. And every time, so we're basically saying the slope is 3. What if the x's, though, were going up by 2's? Would the run still be 1? No, now the x's would be changing by 2's. That would mean our slope would not be 3 over 1, but it would be 3 over 2. So we have to be really careful. I'm not really, I'll have to look at our stuff that we're doing. It's always, our x's are always going up by 1's. But that's why we're always recognizing what's happening with the x's also. If you have a linear one and the x's aren't changing by 1's, then you make sure you're seeking out some help on that and making sure we're getting the right slope. Okay, so in this one, we need an m and we need a b. So what's our m? 3. What's our b?
1. 0.
Go back to what we said before, the starting point. At the starting point,
0.
X is equal to
7.
0, so that
Just
means
kidding.
your y value.
It's 7.
It is, it's 7. B is 7. Where X is equal to 0, what's the y value? Or X is equal to 0, what's the y value? We don't want to have to work this hard. And we could. We could also do something like this. We could say, okay, well, I already know that the slope is 3, so I could do this. I could take one of my points from the table. I could take ordered pair 110, and I could substitute in, and I could find my b. 10 equals 3 plus b. Well, look at there. Subtract 3, b equals 7. So we could find it, but we're such awesome math consumers, we know that where x is equal to 0, that's giving us our b value. So what's our equation now?
Y equals 3x plus 7.
3x plus 7. There's our model for that one.
Are we ever going to learn how to do the quadratic ones?
I don't think so. I don't think we have to. You want to?
No.
Okay. So anybody have any questions or concerns? Anything left over here that you're like, okay, I don't get where we got that? We have an understanding of how we're going to put together linear function names and exponential function names. Okay, then